Hello, my name is Alin Croitoru, and I will present our paper, Self-Distilled Masked Autoencoders are efficient video anomaly detectors. This research is a collaborative effort with Cătălin Ristea, Professor Radu Ionescu, Professor Marius Popescu, Professor Fahad Khan, and Professor Mubarak Shah. The task of abnormal event detection is difficult because abnormal events are highly context dependent. For instance, a truck driving on the street is a normal event, but it becomes abnormal when it is driven in a pedestrian area. Due to this context dependency, collecting abnormal examples is hard. As a result, traditional supervised learning methods cannot be used for this task. Instead, it is usually approached as an outlier detection problem, where abnormal events are unexpected events that happen less frequently than normal events. State-of-the-art approaches for abnormal event detection typically use an object detector to crop regions of interest from the input frame, and then predicting the anomalies at the region level. This pipeline limits the processing to 30 fps, allowing real-time processing for only a single video. In this presentation, we introduce an approach designed to efficiently handle and process multiple video streams in real time. As an overview, to detect video anomalies, we train a lightweight masked autoencoder to reconstruct the tokens with higher motion magnitude. We enhanced this pipeline with self-distillation and data augmentation to improve the performance. We use the absolute difference between consecutive frames to get the motion gradient map. We divide these maps into non-overlapping patches. Further, we compute the maximum gradient per channel, and then the channel-wise mean. And finally, we normalize these values and consider the results as weights, W, in our pipeline. We use W to weigh the reconstruction loss between the tokens of the real frame and those of the reconstructed frame. Visualizing this, given two consecutive frames, we mask the tokens of the current frame. The masked image is processed by the masked autoencoder to get a reconstructed frame. We compute the gradient map as described previously, and then we apply the gradient-weighted reconstruction loss between the predicted frame and the ground truth frame. On this slide, we included an example of our data augmentation method. We extracted anomalies from the abnormal dataset and incorporated them in our examples, creating a set of synthetic anomalies. The synthetic data was incorporated with some probability into the input frame. We utilized these synthetic anomalies in two ways. First, we added a fourth channel to our predictions to indicate an anomaly map, and we always use the normal frame without the synthetic anomaly as the target frame. These modifications imply that the model yields a high reconstruction loss if it keeps the synthetic anomaly in the frame or fails to include it in the anomaly map. Second, we added a classification head to distinguish between normal and abnormal samples, for which we used a cross-entropy loss. Lastly, we included a second training stage in which we froze the previous model and introduced a new decoder, referred to as the student. This student decoder is trained with the same reconstruction loss, but the target is provided by the decoder. As an anomaly score, we use the weighted sum of the reconstruction losses and the classification head prediction. To better illustrate the impact of our model, we included a figure that shows the trade-off between performance and speed on the Avenue and Shanghai datasets. Here we present an ablation study where we can see that all the proposed components are useful. The importance of synthetic data might appear marginal at the first look, but please note that without synthetic data, anomaly maps as target features wouldn't have been possible, and neither the classification head. The quantitative results against methods that don't use an object detector show that our proposed method achieves the best results for most of the considered datasets and metrics. Additionally, it shows an impressive processing speed of 1655 fps. When compared to object-centric methods, our method produces competitive results while offering a significantly better processing speed. On this slide, we included qualitative results for our anomaly maps and teacher-student discrepancies. This is a test video and the anomaly maps predicted by our method. On the last row, we included a graph for the anomaly score. Thank you for your attention. We have a code repository available for our method. If you have any questions, please feel free to ask them at our poster presentation.